Last video we introduced the rigid body approximation and defined angular acceleration. And we mentioned that in the rigid body approximation you could describe the motion of an unconstrained object as being a combination of the translation of its center of mass combined with its rotation about its center of mass. So to that end, now we kind of need to define the center of mass so we know what this point is that we're always so interested in. So let's say we have three particles. I'm just going to call them A, B, and C. And I will go ahead and say put an origin here. So the position of particle A would be RA. The position of particle B would be RB. And the position of particle C would be RC. The position of the center of mass of this collection of particles, RCM, is defined to be literally the weighted average of the positions. So 1 over big M, which this is the mass of the whole thing, mass of all particles, times the sum over our particles of the product of their mass and their position. So this funny bit of notation here, just as a reminder, this is math notation. This means sum over a collection of particles, and this I is called an index. It's going to go from 1, 2, 3, 4 up until however many particles you have. So this would be mass of particle 1, or in this case particle A, times position A. Then we'll add to that the mass of particle B times position B. Then we'll add to that the mass of particle C times position C. Then when we get done with all of those additions, we'll divide by the mass of all the particles. So if you've ever taken a weighted average of anything, this is literally where the idea came from. And when you take this weighted average, you will compute, say, maybe this location right here is where the center of mass of the system of particles is. Now, it turns out that if we just follow through, if we divide both sides by delta t, for instance, dividing this by delta t would give me the velocities of the particles. And so it seems perfectly reasonable to define this to be the velocity of the center of mass, and it turns out to work correctly for what we need. So the velocity of the center of mass of something would be the weighted average of the velocities of all the constituent particles. And then finally, the acceleration of the center of mass is defined to be the weighted average of the accelerations of all the constituent particles. So these particles are all free to move around. They don't have to be rigid. And we can still talk about defining the center of mass. In fact, in certain cases, even when we have a non-rigid system, you can find that in certain cases you can show that the position of the center of mass doesn't change. And so sometimes it's easier if you have already worked out the position of one particle to use that fact to figure out the position of another particle. So with that, just to make it a little more concrete, if we were working in components here, remember that our coordinates all have signs, but the way you would find the x coordinate of the center of mass would be to take the mass of particle 1 times the x coordinate of particle 1 plus the mass of particle 2 plus the x coordinate of particle 2 plus and so forth. And then when you get done, divide that by the mass of everything. And similarly, you can do this for the y coordinate of the center of mass. And if you really wanted to, you could do this for a z coordinate if you needed to, but most of the time we're only worried about working in 2 dimensions. So just to make things a little more concrete, let's try finding the center of mass for a collection of 3 particles. So I'm just drawing some coordinate axes here. So let's say the tick marks here are going to be meters. So 1, 2, 3, 4, 5. This is x in meters. This is y in meters. Oops, -2. Then we'll extend this down. -1, -2. All right. And then again, let's just do 3 particles. So let's say at -2, 2, we have particle 1 with a mass of 4 kilograms. And then at, so now note, again, this is -2, 2 meters. Let's say particle 2 will be located at +3, +4. And let's say it's got a mass of 10 kilograms. Then finally, let's say that particle 3 is located at 2, -2. Oops. Meters. And let's say it has a mass of 1 kilogram. So then our prescription is going to be to find the x coordinate of the center of mass. That will be m1 x1 plus m2 x2 plus m3 x3 over m1 plus m2 plus m3. So the x coordinate of the center of mass will be 4 kilograms times -2 meters, make sure to carry the minus sign, plus 10 kilograms times 3 meters, plus 1 kilogram times 2 meters. And that will all be divided by 4 kilograms plus 10 kilograms plus 1 kilogram. So that's going to be, let's see, -8 plus 30 is plus 22, plus 2 is 24 kilogram meters over 15 kilograms. So let's see, you can factor out a 3. And so that gets us 8/3 meters. And then we can do the same thing for the y component of the center of mass. That's going to be equal to m1 y1 plus m2 y2 plus m3 y3 over m1 plus m2 plus m3. All right, so we can go ahead and put in the values there. So that's going to be 4 kilograms times 2 meters plus 10 kilograms times 4 meters plus 1 kilogram times -2 meters. And again, that's all going to be over 4 kilograms plus 10 kilograms plus 1 kilogram. So this is going to be 8 plus 40. So 48 minus 2 is 46 kilogram meters over 15 kilograms. So looks like I'm factor, yeah, okay, it's not that pretty. It's going to be a shade over 3. It's 3 1/15 meters. So we can locate our center of mass and get that it's going to be a little short of the 2, just titch over the 3 there. So that turns out to be where our center of mass is located. And if you have 3 objects, it will always be the case that the center of mass will be inside the triangle. Okay, so you say, well, that all sounds well and good, but we're not, normally we're looking at rigid objects which have on the order of a mole of atoms in them. So instead of adding up 3 things, we'd have to add up 10 to the 23rd things, and that sounds absolutely horrendous. And you know what? You're right. And in order to do it in general, you would have to use the methods of calculus. But there are certain cases where you can simplify things. So for instance, if you have a symmetric object whose thickness doesn't change, it has been proven that the center of mass is in the symmetry center of the object. So if you have a square, for instance, a square plate, it's in the middle of the square. If it's a rectangular plate, it's in the middle of the rectangle. A circular plate, it's in the middle of a circle, and so forth. So that's pretty helpful in and of itself, but it's actually more helpful than you might think. So let's say that you had an object, sort of a funky L-shaped object like this. So let's say this right here is y equals plus 10 centimeters. We'll say this is the origin right here. This would be y equals negative 10 centimeters. X equals plus 10 centimeters, and x equals minus 10 centimeters. Now, at first blush, you might look at that and think, oh, this is going to be absolutely horrendous. There's absolutely no way that we could figure out where the center of mass is. But it turns out that you can be a little clever about this, because although you can look at this L-shaped thingy, trying to figure out the L-shaped thingy itself would be incredibly challenging. A trick you can do with things like this is a lot of times you can break it up into smaller pieces that you actually understand pretty well. In this case, I can break it up into 3 10 by 10 centimeter squares. And for each square, I know the center of mass of a square is located in the middle. So let's say the mass of this square is just m. This one would be located at negative 5,5 centimeters. This one would have to have the same mass, whatever it is, m. This would be located at 5,5 centimeters. Then finally, this one here, same mass because it's the same size plate, whatever it is, we'll just call it m. This would be located at 5, negative 5 centimeters. And now we can go back to doing the same trick we did before for finding the x and y coordinates of the center of mass. You can say that the x coordinate of the center of mass will be, well, let m1x1 plus m2x2 plus m3x3 over m1 plus m2 plus m3. All right. So all of our masses are just m. Don't worry, it'll cancel. The x coordinate of the first one here is negative 5 centimeters plus m times this is 5 centimeters plus m times another 5 centimeters over m plus m plus m. All right, well, these two here are going to cancel. So we're left with m times 5 centimeters. Oops. M times 5 centimeters over 3m. Cancel, cancel. It's located at the x-coordinate is plus 5/3 of a centimeter. And we can repeat the same exercise for the y-coordinate of the center of mass. That'll be m1y1 plus m2y2 plus m3y3 over m1 plus m2 plus m3. And that will give us, let's see, again here, this is going to be, m times 5 centimeters plus m times 5 centimeters, plus m times negative 5 centimeters over m plus m plus m. Well, that all becomes 3m. These two cancel, 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 and sure enough, 5/3 centimeters. So it turns out that the center of mass of this system is located at 5/3, 5/3 centimeters, and somewhere right about there. So pardon me just a second here before I clobber everything. Let me move. Whoops. Don't want to do that. There. Let me move that. And then I'll draw in my center of mass, which is somewhere around here. Not getting too fussy. This is also a commonly used symbol for center of mass. Alrighty, so it'll turn out that this center of mass will keep showing up like a bad penny. For instance, when we try to describe how gravity rotates an object, we'll pretend, it turns out that you can pretend that gravity is applied at the center of mass. I've already mentioned that in certain circumstances, when you've got a collection of objects, the center of mass of the object doesn't move, even if the individual pieces do. And sometimes that makes it easier for you to figure out where the other pieces moved to. So this is one of those things that's going to keep showing up. All right, so in the next series of videos, we're going to start taking a look at how forces make objects twist, the concept that we call torque. Catch you on the flip side.